Hey everyone, welcome back to Conquering Chem. My name is Nathaniel McLean. Last time we did part 1 and 2, which was about matter and its properties, as well as going into SI units, as well as dimensional analysis. In this part, we will go through density and percent composition, and also go through some of the calculations that will help you for questions in the future relating to these topics. Now, starting off smartly, as we mentioned in the previous part, we said that density is an extensive property of matter, meaning that no matter how much or how little is there, the density of a certain piece or substance will always be the same. So for example, if we were to take a block of water that is 1 centimeter times 1 centimeter times 1 centimeter, or 1 centimeter cubed, and we place that on a scale, it would always equal to 1 gram because the density of water is 1 gram per centimeter cubed. And it doesn't matter if you have a bucket of water, a cup of water, or an entire ocean, the density of water will remain the same no matter what. So moving on smartly into density, as we said before, density is a ratio, mass to volume. So it goes without saying that to calculate the density, we would take the mass and divide it by the volume. Over to the right of the screen, we have the density triangle. Be sure to memorize this because it will be very helpful in all of your calculations moving forward. And it's easy to remember. DMV is how I like to remember it, just DMV. And remember that the M is on top in the triangle. And it basically tells us that if we want to find the density, we look at the triangle and we see that the M is over the V. So the density is equal to the mass divided by the volume. Now, if we want to find the mass, we would simply take the density and multiply it by the volume. And if we want to find the volume, we would simply take the mass and divide it by the density. And before moving on, as I have at the bottom of this page here, sometimes you might see the symbol P for density. That's one of the official symbols for it, so don't get confused. For now, we will stick to D. Now, jumping straight into a problem. This question reads, what is the density of a regular block of wood that has a mass of 2,500 grams with a length of 1.10 meter and a width of 9.5 centimeters and a height of 5 centimeters? Now, this is a whole mouthful right here, but what I like to do with every question is to break it down. So I break it down into 4 main parts. First, you want to know what the question is asking, or what do we need to find? And in this question, we're being asked to find the density. What is the density? Next, I like to ask myself, okay, now that I need to find the density, what do I need to find the density? Meaning, what parts make the whole that is the density? And so from the triangle, I know that to find the density, I need a mass and a volume. Knowing that I need these here, I look at my question. Is there a mass? Is there a volume? Well, I see a mass, 2,500 grams, but the other information I was given was lengths, which is what brings me to the next question. What information was given? And knowing what information was given, we now have to say, what can this information lead us to that we need? Or how can I find the volume, which is the missing factor for this question? And to find that volume, we can use the lengths which were given. Knowing our equation, first we find the volume. Now the volume is going to be equal to all of the lengths multiplied by each other. In the previous part on dimensional analysis, we know that when we do our calculations, the units have to be constant. So if we have a unit in centimeters, all of our measurements have to be in centimeters for the question or the result to work out. So we would convert our 1.1 meter to centimeters here, and overall we would get 5,225 centimeters cubed. We get centimeters cubed, again, because we're multiplying centimeters times centimeters times centimeters. And now that we have our volume, we can simply plug that into our equation, given that we already have a mass, giving us an overall density of 0.4785 grams per centimeter cubed. Of course, feel free to rewatch this. I'm also going to be posting some tutorial questions as well, in addition to these examples that I show in the lecture video. So I encourage you to watch those after this video has ended as well, to get a better understanding of how to do these calculations. Now, moving on to this question, a little bit simpler, but it can still be tricky depending on how you look at it. And I would challenge you to try to do this question on your own. So if you want to, pause it here and then continue to see if you got the right answer. But continuing, the question reads, what is the volume in liters occupied by 50 kilograms of ethanol at 20 degrees Celsius? And what we know is that the density of ethanol at 20 degrees Celsius is 0.789 grams per milliliter. So going on again from the 4 questions we ask ourselves, what are we looking for? Well, this question states it clearly. We're looking for volume. What do we need to calculate volume? Well, we need a density and a mass. What was given? Well, here we are given both the mass and the density. So lucky us, we don't need to try to figure anything out. And so going on from here, we can simply do the convergence using dimensional analysis. We know that we want an answer in grams, so we convert our kilograms to grams using our conversion factor. 1,000 grams is equal to 1 kilogram, so 1,000 over 1, giving us our 50,000 grams in the end. And now that we have our mass in grams, we can then use our density triangle over here, trying to find the volume. We know that volume is equal to mass divided by density. So we have our mass, we divide it by our density, and we have our final answer right here, 63,371 milliliters. Now, here is where a lot of people can slip up because the question asks for an answer in liters. So the final step would be to convert those milliliters to liters by dividing by 1,000 milliliters. And there we have it. Now moving on to percent composition. The percent composition of a sample of matter is the number of parts in 100 parts of that whole. And so to explain this a little bit better, let's say we have a cup of salt water. Now that salt water could have a 5% salt water concentration. And what that means is that for every 100 grams of salt water, there are 5 grams of salt within. Which means, again, explaining further, that if we were to break that into parts, 5 parts of that water would be salt or sodium chloride, which is salt, and 95 parts would be pure water. This can be expressed in a number of ways depending on how you need to do your question. So again, jumping right into an example, a 75 gram sample of sodium chloride is to be produced by evaporating to dryness a quantity containing 3.5% sodium chloride by mass. How many liters of seawater must be taken for this purpose? And the density of the seawater is 1.03 grams per milliliter. Again, a lot went on in this question, but we can break it down into parts. What are we looking for? We are looking for liters or a volume, and more specifically, we're trying to figure out what volume of seawater must be used to make 75 grams of sodium chloride. And there are a number of ways to break this question down even further, but I will just show you the way that I would do it. And my step 1 would be to determine the mass of seawater that contains 75 grams of that sodium chloride. Because again, to find a volume, we need a density and a mass. So if we find the mass of seawater, we can easily convert that to a volume. And secondly, I would convert that mass, as I said before, to a volume using the specific conversion factor, which in this case is the density equation, along with whatever conversion factors are necessary when we do our dimensional analysis. So let's see what's done here. Our yellow shows how we find the mass of seawater that is necessary. So knowing that we need 75 grams of sodium chloride, we multiply that by the percent composition of the seawater, which we know is a 3.5%. Remember that 3.5% saltwater solution means that we have 3.5 grams for every 100 grams of seawater. So when we multiply these together, we would get how much mass of water would be needed. Now our green shows how we convert that mass to a volume. Why is that? Because we know that volume is equal to mass divided by density. So after we find the mass in yellow, we can easily divide by the density of water, and in this case, because of dimensional analysis, it looks like multiplication, but you are simply dividing by the density of this water, which is 1.03 grams of seawater, and this last step in purple simply converts our milliliters into liters for our final answer, leaving us with 2.08 liters of seawater. This question can be further broken down in one of my tutorials, where I can explain it even further if you didn't get it here, so feel free to watch that. This is the end of this part. I just wanted to introduce percent composition and density. I hope that this helps you. I look forward to seeing you again in part 4, where we will talk about uncertainty in scientific measurement. Namely, we'll be speaking about accuracy, precision, error, and of course, introducing you to significant figures and exponential notation, which again is another skill that is necessary for concurrent chem, or at least general chemistry for now. So thank you again. My name is Nathaniel McLean. This is Concurrent Chem. Feel free to visit my Patreon where you can get breakdowns of all of these questions and lectures. Also, you'll have early access to any of my videos, all of my tutorials, and all of my PowerPoints, and you'll even be able to download my PowerPoints and tutorials and the breakdowns of each question. So thank you again, and see you next time.